All right, good afternoon. I'm Yousry Azmy. Have a group here at NC State that is the Nuclear Computational Science Group. If you're not familiar with what nuclear computational science is, it's basically a good combination, a good mix between three elements. The physics or engineering level, reactor, detection, system, whatever. The application that you're interested in. It has a good dose of mathematics, analysis, understanding of the numerical methods and the algorithms that are used to solve this particular problem. And then computer science, because ultimately you want to take whatever it is that we develop, put it on a computer and get a decent solution. So understanding how this is workable on an advanced computational system. The general, before I get into the nitty-gritty, the general direction or program for the research that we do in my group is based on or seeking the development and application of numerical methods. This is where you take a differential or integral differential, in our case, equation and apply discretization methods to make it a numerical method that then you can throw on a computer. This is much of what Dr. Anistratov was talking about also, so we have a lot of commonalities. Then we take these methods and we apply some analysis, mathematical analysis tools to understand the error that comes out of this discretization. We also apply performance modeling and analysis to understand when you actually take this method, put it on a computer, what do you get and how well do you get it right. And then very infrequently, but it happens sometimes, that we approach a specific application that has a challenging transport issue, and we devise a very specialized, innovative method to address this challenge in the most efficient computational approach. And I'll show you an example of that. The centerpiece of the work that we do in my group is the Thor Code. Thor is a code that was developed when I was in Penn State, but I brought it with me here and is now maintained in my group. It's basically the transport equation solved in steady state using the multi-group energy discretization, using discrete ordinates for the angular discretization, and using unstructured grids tetrahedra in particular with the short characteristics, the arbitrarily high order transport characteristic method for the spatial variable. Thor has features like every code, so we do have a decent verification suite to check when we put something new in Thor, and this has been developed over the years initially via an NUP project, and then we continue to do that. There is an ongoing validation exercise, so every time we meet a new problem that is worthy of transport solutions, we try to develop a validation exercise to gain some confidence in the applicability of Thor and the underlying nuclear data to these new configurations. It's capable of solving fixed source as well as criticality problems, and there is a whole bunch of ways of solving the criticality problems. And it has some advanced features to break cycles. These are very peculiar things that happen specifically in unstructured grids that are generated automatically. So I'm going to go very quickly over the types of projects and recent research, whether current or recent, that has happened in my group recently. The first picture here is from an experiment that was done in the DAF facility. Sorry, this is in Oak Ridge. And it's basically this is one of these examples where we devised a new way to solve a transport problem. Here is where you would have the hold-up problem. You have a source of radiation in an enclosure. That enclosure could be a big hangar or something. You're talking about literally tens, maybe hundreds of cubic meters. and you don't know where the source is. So we use a Bayesian predictive modeling capability to be able to locate the source, both in space and in energy distribution. And this picture here is an experiment that one of my students did at Oak Ridge in order to measure results based on which we could validate the DIMP. DIMP is the name of this approach that we devised for that. So the second application here is a residual estimator. This is an error estimator that one of my students developed. And you want to know the error, of course, for multiple reasons. One of them is to be able to quantify the confidence that you have in the correctness of the solution. And what you see here is a distribution of the error estimator divided by the true error for a given problem. And it shows where, locations where the error is good and locations where the error is not terribly good. Here we're not interested in where the error is big or small. Here we're interested in how well we can estimate the error, whether it's big or small. This is a research by a student who finished his master's recently. Ray effects is something that, a defect basically, that affects discrete ordnance methods. So this student developed a Monte Carlo approach to compute the nth collided flux source. Nth collided source to decrease the effect of ray effects. Ray effects here in this particular problem, where you have a source in the middle of an air enclosure. If you think through the problem mentally, you'd see that the maximum flux should be at the center. Here you see that it's at the corners because we're using an S2 quadrature. With the same S2 quadrature, if you use the fourth collided flux, you see that you've moved back the peak to the center. This is the work of another student looking at angular discretization error. So just like we are interested in the error from the spatial discretization, we're also interested in what happens from the angular discretization. Here are a bunch of quadratures, and you see that asymptotically the standard or the traditional quadratures have first order convergence. This is deceiving a little bit because ultimately these come back and become asymptotically quadratic. Quadratic is still better than linear, so we learned something here. This is a validation of Thor. This is where we use the this is a plutonium ball, weapons grade, and the student actually made measurements of this and compared using the mitigation for ray effects method that I showed you earlier. He shows that with increasing number of collisions, you can approach the correct answer way better than if you went with the just increasing the number of collision angles in a quadrature. I'm not going to go because we're running out of time. This is a case of a student who did massive parallelization, up to 32,000 processors on Jaguar PF. And his interest was in figuring out why the black and the green line grow way too fast. In a weak scaling, ideally you should see a constant change with increasing P, and it turns out to be communication, so he's looking at ways to fix that issue. Here's a hybrid acceleration method to improve the convergence of the inner iterations in a discrete ordnance calculation that is based on asynchronous spatial domain decomposition. Why are we interested in asynchronous? Because it alleviates the burden of determining in advance the sequence of a sweep if you had a synchronous spatial approximation. This is self-explanatory. It's basically visualization and automatic mesh generation techniques that go hand in hand with Thor. Thank you.